This is my Physics 1 lab report for Lab 2. So the purpose of this lab is to observe the motion of an object that is thrown and moves like a projectile. In this case, we threw a paper ball, which is a system, from one part of my table to another. The surroundings in this case are the gravity, air around the ball, the rest of the room, and the drag from the air. The fundamental principles that we talk about in this lab are Newton's second law, also known as the momentum principle, which relates the net interaction between the system and the surroundings to observe the motion of that object. We use the velocity and position update formulas to predict the future movement of that object using our initial conditions. We also considered the gravitational constant and drag force as part of our FNet. So these are the main results. The red line shows the computational model with only gravity. The yellow line shows a computational model with both gravity and drag force, and the blue line shows the experimental data. As seen in this big graph, we can see that the red line veers very far from the experimental data as well as the yellow line. However, the yellow line and the blue line are very similar, indicating that that model is a better fit for our experimental data. And as seen in this top graph, there is some differences, and we will discuss those on the next slide. So comparing all of these, the blue line, which is the experimental data, shows the trajectory of the ball in real life. While there are some bumps in the graph, this mostly just indicates that there's human error while using the center of mass tracking. The computational model with only gravity has the same shape as the trajectory of the ball in real life. However, the magnitude of that movement is much larger, indicating that the gravity alone isn't a good predictor of trajectory, and rather that there are other factors acting upon that ball. And that other factor is drag force. So in the model with both gravity and drag force, the slope of the graph is very similar to the experimental data. However, that position is a little bit lower, which is most likely, again, due to human error. So these are our initial conditions. The ball is 10 grams, which I converted to kilograms, so 0.01 kilograms. The initial conditions of the initial position vector comes from tracker, and then the initial velocity was calculated using the v-average formula. The initial time, as well as the delta t, was also taken from the data in tracker. So this is the code when only considering gravity. What you'll notice is that FNet is just the gravitational force. And we come down here to draw arrows for the drag force. We multiply by a vector of 0 since that's not something we're considering in this graph. While looking at the code for the gravity and drag force, you can see that I split up the gravitational force and the drag force and then added them to get FNet. And the reason I did this was because in these arrows, the gravitational arrow has to be multiplied by only the gravitational force, and the drag arrow is multiplied only by the drag force. And the main reason that we make these models in the first place is to show us how the trajectory would look if there weren't any human errors, and to help us isolate some other factors, because there can always be other factors acting upon the system in real life. However, in a model, we can isolate those and only focus on the components that we want to look at. So any errors in this experiment can be attributed to rounding errors, human error in the center of mass tracking, and human error in using the calibration stick. So what does this all mean? The model with both gravity and drag force predicts terminal velocity really well, since the drag force and gravity balance each other out and to get an approximate net zero, and the object is still moving without speeding up. Now the graph that shows the gravity only without the drag force shows that we do not have terminal velocity in that case, and the ball will continue to free fall while speeding up. And what if we threw the ball straight up and then it fell straight down? Well, the time would be much longer in this case, since the object has to travel twice the distance, both upward and downward. On the right side, we can see that the arrow pointing down is what is similar to what we calculated in this lab, and which has a time of t. And on the right side, we can see what would happen as the ball would travel upward, and that also has a time of t, since it has the same distance. And so if you add those two together, you get 2t, so the time is twice as long. Thank you.